Hello, and welcome back to another video with It's Dr. Dan, and today we're going to be learning about the concept behind colligative properties, which relates molality, a concentration term for solutions, and how these different solutes are going to be dissolved and dissociate in solution. Now, when they dissolve, what happens is they break down into individual ions or particles, which can disrupt the intermolecular force networks within a solvent. Now, when that happens, there's all sorts of different unique properties that you probably take advantage of in your everyday life that get manipulated as a result. So just to kind of give you some ideas of these, so a lot of them are actually things you probably do around you right now, possibly. So let's say when it's really cold in the winter time and you need to salt the roads. Well, the reason that they add salt to water, which is the solvent, it's going to disrupt the hydrogen bonding that occurs between water. Therefore, it makes it really hard for water to freeze because all those little salt particles are causing ion dipole force to have. It lowers the freezing point. It changes it. If you add antifreeze to a car, the more of adding the solute, it does something a little bit similar. It makes it so it's harder for the car to either overheat or even freeze on you, so that way your engine doesn't have any kind of weird effect. It changes that boiling point, it elevates the boiling point and lowers the freezing point. Another concept is if you love to eat different pickled foods, so like maybe if you like pickling jalapenos or just making pickles or any of these types of different crunchy foods, well, essentially these different substances absorb the water out of all these different molecules, and in the process cause them to get a different texture change. It changes their flavor. It has a major effect on how we can see them. And that's what we're going to be talking about in this video, is how all these different properties are affected by the solute solvent interaction. So let's take a look at it and stay tuned, and please feel free to learn all about colligative properties. Let's take a look. The first concept we're going to talk about is boiling point elevation. So now what this is all about is when you dissolve a solute in a solution, it's going to actually increase the boiling point of the solution. So it's going to get elevated and go up to the sky. Now, why does this entire thing happen? So what we want to think about is molecules, when they are in solution, can it change the boiling point? Why would that happen? Well, what this implies is that that means it's more difficult for a molecule to go into the gas phase, right? When something boils, it's going from a liquid to a gas. So now why would this all happen? Well, we got to try to remember that intermolecular forces are at play when we are talking about these solutions, right? Waters are hydrogen bonding to each other. There's an interaction here, meaning like dissolves like. So if I add a solute to the mix, well, what's changing here? Well, instead of hydrogen bonding that is possible, now we're going to have ion dipole forces, which are possible, which, if you remember, ion dipole forces are stronger than hydrogen bonding, meaning that they're going to have a preference, and it's going to change how these are interacting. Let's take a look exactly what I'm talking about here. So the way that we look at this, so if I have a solution that all these individual water molecules are all hydrogen bonding together, they're interacting, they are holding each other inside the liquid phase, meaning that it's actually very difficult for them to become a gas. It takes a lot of energy for that to happen, right? In order for something to gain enough energy to go in to be vaporized, it takes a lot of energy to do so. So when you have, let's say, something like water, it usually takes it's about 100 degrees Celsius for it to be boiled. Now, if I decide to add salt to water, which you do all the time when you make pasta or rice, well, most of us do it because of the flavor profile, right? We like it when the water actually has a little bit of flavor to it. Now, the other reason you do it is because it actually can raise the boiling point slightly of water, meaning that it will cook your pasta or rice at a slightly higher temperature, therefore maintaining also the water level inside the pot as well. Now, what is exactly happening there is essentially, if I take these little yellow dots here, which you can kind of see all around here, these are your solutes that are inside of the solution. So solute, as in these are your salt ions. So like you can pretend they're like Na plus or chlorine or whatever ion you want to pick. Choose your favorite. Now, when you place those into solution, now you have ion dipole forces. These are much stronger as a result. They're tougher. They're something that's a much higher force than hydrogen bonding, meaning it's harder for them to let go of water. They don't want to let go at all. When essentially you have a liquid, one way to kind of think about it is when they're trying to be a gas. It's like essentially if you were to try to pick up a kid at a sleepover and they've been staying there all night and they're like, please don't take me home, don't take me home. Well, it's a very similar concept here. The salt is going to be holding on to the water molecules. It's like, no, it doesn't want them to leave. It's a similar idea. So the stronger the intermolecular force, the harder it is. So the question I would ask is, how does the presence of a solute affect the kinetic energy of water trying to boil? And essentially, it requires more of it to happen. It holds things back because the forces are stronger. It's going to take more temperature to be able to leave the gas phase. And that's one way we want to think about it and as we move forward. So with this concept, just to wrap it up, so one way that we can look at it is solutions will have a higher boiling point than pure water. So pure water, its general boiling point is around 100 degrees Celsius. So I drew a little line here to help illustrate that, hey, this is at 100 degrees. So the second that we end up adding some salt or a solute to water, what's going to happen is you're going to see an overall increase of that temperature. It's going to go up as a result. So let's kind of maybe draw that as white here instead of purple. So it goes up. Now, if I add more salt and it dissolves, so the more and more you add, that temperature is going to go higher. So one thing that we see here is the higher the concentration, the more the temperature is going to raise. So higher a concentration is a higher temperature, okay? Now, when it comes to a higher concentration, we measure this for colligative properties in molality when that happens, okay? So that's a cursive M when we talk about molality. And the higher that is the higher temperature that is behind it. So the more concentration, more temperature, because it's holding those molecules back. So let's take a look at all the concepts we need here to be able to determine colligative properties and how it affects things. So the first concept was that higher molality means, aka more solute, has a big effect on colligative properties. Now, this isn't the only thing we're looking at as well. We have to remember that solubility is important as well, meaning how do these different molecules, how do they end up actually like breaking apart in solution? So one thing to think of is the more soluble the particles are, or the ions, the greater the boiling point. So what we have to do is understand how we can write solubility equations. So I have a couple here, and what you are going to be doing is you need to count how many different particles or ions are formed when it is soluble. So is understanding electrolytes as well, which if you need a review on that, go back to my other video on electrolytes to be able to understand that. So what we're looking at when you write out your solubility equation is you're counting how many particles are formed. So let's say if I look at this first one, we have glucose, which is a non-electrolyte, meaning that it does not become ionized, but it's polar, so it's dissolved. So when that dissolves, notice how we just have now aqueous glucose. So what we are going to do is count how many particles were formed. And what we see is, well, there is one particle formed. So what this means is that it has an I equal to 1. Now to go to the next one for counting again, if I take sodium chloride, it's soluble. So it's going to break down into sodium and chlorine as my two ions. And how many do you have? Well, we have 1, 2 ions. So that means you're going to have an I value equal to 2. We're just counting. Now, if I do the next one, calcium acetate, well, This one we have 1 calcium forming and 2 acetate ions, meaning you have a total of 3 particles that are formed. On the last one, we have iron chloride. So it's 1 iron, 3 chlorines that are here. This one is going to be I is equal to 4. Sorry, the last one was I is equal to 3. This one's I is equal to 4. All right, so we're adding the coefficients together. Now, why is this important? Well, the effect here is the more particles you have in solution is the more disruption that's going to be caused within the intermolecular forces. So one thing that you're going to see is the higher the I value, the higher the boiling point is going to be. So essentially, as we're kind of moving this way, right? So down towards more I values, we're going to have a higher boiling point on the bottom. So the more ions, the higher the boiling point. And this is going to take a higher priority over the concentration as well. If your concentrations are very close, let's say if we had all 4 of these solutions, well, and like maybe if it's like all like 2, for example, the I is equal to 4 will have a greater impact because they're all about the same. So usually we always go by how many particles are being formed. So what is your ionization factor? Can you count, right? How many ions are there? And then if you need help with solubility and understanding how to use solubility rules, refer to my other videos in this playlist to be able to master those skills too. All right, let's take a look at the next concept. Freezing point depression is the next one. So if the boiling point goes up, the freezing melting point can go down. So it's the same idea here. If we dissolve a substance in water, so it will lower the freezing point, especially when you compare it to pure water. And when I say pure, that means that it's the only substance in that water. Now, why does that happen? Well, when we add, let's say, a solute to the mix, it's going to prevent hydrogen bonding, where you see we have a little solid hydrogen over here as an ice cube, right? When you add ions, it stops it. This is why they salt roads during the winter in colder climates, because, you know, ice is a big hazard for when you're driving, cause you to slip, it cause crashes. But if you salt the roads, it will help prevent it from freezing, or it'll take a lot longer. So usually you'll see a big layer of salt all over the roads and during winter time, like in the northeast of the US or in Europe, or even in northern or the northern Midwest, even in the mountains around California, you will see them salting the roads. So when this happens, well, it's going to be the same idea, but opposite of what you saw earlier. So pure water freezes at about 100. And then if you add a little bit of solute, well, it would go down, let's say a little tiny bit to maybe just a little lower than the freezing point. You'll see it maybe about by a degree or 2 typically. It depends on the solute. So this is solute specific. In our course, I'm not worried about you guys calculating it, but if you have to take general chemistry, that is something that you will have to calculate. But it's a pretty easy formula to use. It just goes off the number of particles, times that by molality, and then times a constant. The last concept is on osmosis. So when you are trying to learn about osmosis, this is a very important concept for anyone interested in the health sciences and biology, because this is a huge concept that's used for how your body functions, especially for how your cells work. So all this is about how a semi-permeable membrane, which means when we say permeable, means that something can pass through it. Now it's to some things, that's why it's the semi part of it. So it allows certain molecules to pass. All your vital organs and your cells usually act like a membrane. So now how is it semi-permeable? Well, what happens is that water can move through it, but nothing else. So I have 2 sides of a chamber here, and then this black line in the middle is my membrane right here. Now what's happening is that water can move from the left, it can move to the right, it can free flow between the 2 sides. It's like in a dynamic equilibrium when that happens. So when we say that water is free, it's because it can move where it wants. However, we're talking about colligative properties. So what happens if I add a solute? So when we add a solute, water favors dissolving it, meaning that if I have NaCl, it will want to dissolve it. It will rush to it. it will clump around it. So what will happen is if I have, let's say, an area of high salt concentration on the left. So you see the purple and the green dots here. So there's more salt. So what's going to happen here as a result? The water is going to rush through it. And if you remember, this semi-permeable membrane, it allows water to pass. So all of the water is going to go from an area of low salt to high salt concentration. So it's all going to go in towards the left-hand side as a result. So let's see what this is going to look like. So what you're going to see is after that raises, all the water all of a sudden is all on the left. Notice how much higher it is. So if you can imagine this as a cell, it's going to be a lot plumper of a cell as a result. So it's going to all build up. This is known as osmotic pressure when it all goes on one entire side. So this is why you need to make sure you regulate your salt and sugar levels in your body, because water can rush from one area to another. So if you're diabetic, or if maybe you have very high salt levels in your body and you need to watch your food, this is the reason why, because you can imagine how this might be applied to cells. So let's take a look at applying this to biology then. So when you eat or drink, one thing that's going to happen is that your intestines are going to act like a semi-permeable membrane. So generally what they'll do is they will take out all the water that you drink in will get brought into the body. So here I'm kind of showing how water is flowing into the body. So usually whenever you drink a lot of water, what's going to happen is your body tends to have a higher concentration of solutes. So it's going to flow out. It's going to hydrate your cells. But what about, why do you always drink fresh water? Why can't we drink salt water when there's so much of it on our planet, right? 97% of the water is salt water. Wouldn't it be great if you just drink it the way it is? Well, the reason is why you can't do it is because of osmosis. So if you were drinking a very salty liquid, so think of if your intestines were full of salty water, what's going to happen is because of osmosis, it's going to flow from an area of low concentration to high concentration. So if your body, for example, is considered to be low concentration, so let's just say low, and what we have on the inside is high. So we'll write high here. It's going to all flow out of your body and dehydrate you. So if you ever drink salt water, not only does it taste gross, but you're going to start feeling extremely sick because all of your cells do not have enough water. And this can be a really big problem with red blood cells. Let's take a look at that. So when it comes to your blood cells are something that can be extremely affected by the amount of salt and sugar in your body. So when you're giving IVs to maybe a patient in the hospital, they need to make sure that the levels are appropriate for your patient, so that way their cells are healthy and hydrated and happy. So one thing that you're going to see here is there's 3 blood cells in front of you. We have an isotonic cell. Now what that refers to is that the level of essentially the concentration of salt and sugar are normal inside and outside the cell. So what's going to happen is pretty much the water is going to flow in and out nice and happily. There's going to be no issues at all. The one on the top in the middle here is known as a hypotonic situation. So this is when you have essentially a very, very low sugar or salt in the body. So let's say if I kind of write next to it is if I have low sugar in the body, so around it, so it's in a hypotonic solution. Well, what's going to happen is inside of your cell is typically always 0.9 and 5%. So let's say if outside the cell, it was like 0.4% and 4.5% sugar, salt and sugar respectively. What's going to happen is all of the water that is now outside is going to rush inside of the cell. It's all going to come in. Now, when that happens, your cell is going to blow up like a big balloon. And as a result, it could pop and ends up actually killing your cell essentially if you have a too big of an imbalance. So for people who might be diabetic and have really low blood sugar, this is one of the reasons why they're feeling very lethargic, is because their cells are not functioning properly. It's not at the right concentration. So it's very important to regulate levels. Now, the other option is, let's say if I have my cell, and let's say on the inside of the cell is normal and everything's happy. So we have 0.9% and 5% for salt and sugar. Now, if the outside is, let's say you drink a lot of really salty foods and you have a lot of different sugar and cake and all kinds of really good stuff, well, what's going to happen here is the opposite effect. Remember, from low to high. So when that happens, we have really low concentration inside and everything's going to come out. Therefore, we have a hypertonic cell, which is when it's going to dehydrate your cell and cause it to collapse in on itself, losing its function and its purpose. So this is some of the factors that can happen because of colligative properties. So let's sum it up. So to sum up everything, the most important concepts that you need to know is first is counting how many particles that you have when you write your solubility equations. So you have to write how they dissociate and fall apart when they are dissolved. Depending on the number of particles, the more of them, the more of an impact that your solute will have on the property of the solution. Now, next would be molality. So that would be the second thing. So if the particles are the same, check on the concentration next. And if they're both the same, then you look at if it's an ionic molecule versus covalent. Ionic has the stronger impact. Now, when we're looking at what properties it has, the solute will lower the solution's freezing point, so we can have freezing point depression. Now, like I said, that's proportional to molality. Your solute can also raise the solution's boiling point, so that's why we add antifreeze. So that way it helps prevent your car from overheating and can also prevent it from freezing up as well. And then the last one is that solutes can draw water through membranes, meaning pickling, right? So pickling or antifreeze or any of these. So you have freezing point depression, boiling point elevation, and osmosis. And that's what you need to know for colligative properties. Okay. So thank you so much for listening. As always, I appreciate all of you for whoever watches, and hope you all enjoyed this. I hope it helped you understand this concept a little more. Please, if you have not already, please like this video. It helps me grow. And comment below if you have a question. I would love to help you as well. So, and if you haven't yet too, subscribe to the channel too. All right, y'all. I hope you have a wonderful day, and I'll see y'all later. Bye now.